Hello, I'm EnterElysium, and welcome to Kerbal Space Program 101! Well, today it's 102, Orbital Maneuvers. So, this is going to be the basics of doing orbital stuff, moving your orbit around, fixing bad orbits. So if we have a look at the map screen, M for map screen of course, you can see we have a lovely equatorial orbit of 99.26 by 99.87. So, within 600 meters. That is called a pretty good orbit. If you're within, 1%, that's a pretty good tolerance. Now, let's talk about how we can change this. So I want to start from a perfect orbit so I can screw it up, and then you can see how I screw it up and what effect it has, and then we can revert it. So what we're going to do right now is we're going to show how to move periaps and move apoaps. So, let's have a quick talk about directions in space. So, in space, like anywhere in our universe, it's three-dimensional. 3 dimensions. We have 6 directions, we have forwards, backwards, up, down, left, and right. In space, you can orientate them however you want. What we're going to do, though, is we're going to orientate them according to our orbit. So we have, you might have noticed down here, we have some things next to stability assist. T to toggle stability assist. When we have it on, you can see these buttons as well, and you can also see these markers on the nav ball. So let's talk about them. This one is retrograde. Well, this one's prograde, and that one's retrograde. These are diametric opposites. So, prograde, if we click it, it should take us towards prograde slowly. It's a very large craft. I should probably get rid of the booster section at the back. Let's actually do that now. There we go. I don't really need the fuel. Got plenty of fuel. This is a ridiculously sized craft. So, here we can see, let's just warp and unwarp to, there we go, point. We're pointing prograde. Prograde is along our velocity vector. So, prograde is this way. Forwards, along a velocity vector. Our velocity vector is going around the planet. Velocity means speed, except it's got a direction, so you can say, I'm going 10 meters per second. With velocity, you'd be like, I'm going 10 meters per second, or minus 10 meters per second. In this direction, that would be a velocity. So we're going along our velocity vector. That would be our prograde, forwards. If we point retrograde, you can probably guess what it is. It is, yep, we're going directly behind. Retrograde is behind us, okay? So that is what retrograde is. So prograde is along a velocity vector, retrograde is away from our velocity vector. And like you might guess, you can burn prograde to increase your velocity and retrograde to decrease your velocity. I'll go into them in a little bit later, but I'm just going to go over the terminology now, so don't worry. I'm going to throw some words at you, and then I'm going to use them later. So if you need to, skip back to this point in the video to remember what the terminology means, go ahead. We also have normal and anti-normal. Normal and anti-normal are, I call them a little bit different, right? Because normal and anti-normal, if you imagine our orbit here, it's obviously, it's a circle. So you can project it on a plane. We could have a plane, like a 2D plane, like a flat sheet of paper, and you could draw your orbit on it, right? It's basically a circle right now. It's technically an ellipse, but it's very close to being a circle. You could draw that on a piece of paper. Normal and anti-normal, and what happens if you say you stick a pen in the piece of paper? It is at normal to the piece of paper, which is, perpendicular to. So if I were to point normal, you'll see us pointing, let's just get this perfect lined up, upwards, and anti-normal will be downwards. There we go. We're pointing normal, and we're wobbling around because Kerbal Space Program's stability system is pretty awful at pointing at the different nodes. There we go. Normal. Normal to the plane of our orbit. And if we were to point anti-normal, we'd be pointing downwards. There we go. So, basically, normal and anti-normal are for pointing up and pointing down. And you can probably infer what they will do, but we'll go over that in a second. By the way, use the warp and, warp forward as warp down when you're using these nodes, because it will consistently overshoot. I just think it's kind of necessary. The stability system isn't particularly clever. We also have radial and anti-radial. So, the radius of a circle is, the distance from the center to the edge. Radial, I just imagine an extension of that. It's outwards. It's outwards from the radius. So, radial is pointing away from whatever you're orbiting, well, the point you're orbiting around. And anti-radial is pointing inwards. So, we should be pointing, ta-da, away from the planet. And if we point anti-radial, we'll be pointing downwards. Down is very subjective. I really shouldn't use the term down, because downwards in terms of gravity, but not downwards in terms of the ship's orientation or, the orbit. Down can mean several different things. So that would be our anti-radial right there. So, those are the 6 directions, the 3 dimensions we have. How are we going to use them? So every time you're orbiting, those 6 dimensions are relative to your orbital path. It doesn't matter where your orbital path is, they're relative to it. So, how are we going to use them? Well, if we want to decrease or increase our periapse, let's do something really simple to begin with. So say you had a really high or really small periapse, and you want to change it. Well, one way to do that is, and like I said before, anytime you want to do anything, you want to do it at a maximum or a minimum to get the most effect. You want to take advantage of what is called the Oberth Effect. So we're going to get to apoapse, and then say we want to increase our periapse. Say we want to go up to 120 kilometer orbit, 150 kilometer orbit. Let's point prograde. Prograde at apoapse. We're actually going to overshoot apoapse a little way, but it doesn't matter too much. This is just a demonstration of what the different orbital mechanics do. So if we point prograde, which is taking us drastically long time, this is a fairly large, heavy craft. There we go. Prograde, and we burn forwards, it will increase our periapse. And you see it's flipped over now. Our periapse is actually where we are, and our apoapse is on the other side, because the apoapse is now higher than the periapse. So let's increase that, because apoapse is defined by being the highest point in your orbit. Let's go to 150, why not? By the way, you can see it moving around slightly, and that's because we're burning after a maximum or minimum, so we're burning after periapse. 155. Yeah, that works. So that's how you decrease or increase a periapse. You do it at the opposite point. You can do the same with an apoapse. If you want to decrease an apoapse, you burn at periapse. And likewise, so if we were to, burn now retrograde at periapse, we'd decrease our apoapse. So basically what happens is, you want to increase your orbital speed. So I'm going to sort of knock this down to a very rough shot approach. This is our orbit. Okay? Right here, we're going very fast. And the reason we're going around an orbit is because we've got this speed in this direction, right? We've got speed going in this direction. That's our velocity of our travel. But we also have a velocity pulling us down. We actually have an acceleration pulling us down. It's called gravity, as you probably know. We're going this way, but we're also going this way. The resultant is we're going this way. And then, we project that to here. Where are we going? Oh, we're going that direction, but the acceleration is also pulling us down. So where do we go? We go here. And we continue doing that, and you just iterate it enough, and it will be a circle. So we could draw this as a hexagon, we could draw it as an octagon. You have a force pulling you that way, a force pulling you that way. Well, you actually don't have a force pulling that way, you've got just direction of travel, but you get the idea that you end up going effectively around and around and around and around. So, what happens if you were to increase the speed in that direction? So increase your velocity in that direction. Well, it wouldn't be as, it would be bigger compared to the acceleration. So you're going to go more in that direction. So you're going to get away from the planet. So if we burn prograde, our apoapse goes up. I don't know if that makes entirely sense. That's how it figures in my mind, but it might not work for some of you. So that would be how you increase your apoapse. Likewise, if you burn retrograde, so let's just point retrograde. It might take a little while to flip over. You will decrease your velocity. So if we decrease our velocity, we're no longer going that way as much. The planet's actually got a bigger pull, which means that we're going to go down. I really wish it didn't overshoot the maneuver nodes. It's annoying. Right, let's... And you will see apoapse is starting to fall. So we can do that pretty harsh. Now, of course, we want to do this at apoapse and periapse. I'm just showing you a very rough shot approach. We're going to sort this orbit in a minute. So, that would be how you increase and decrease your apoapse and your periapse. You burn at the other one. If you want to decrease your periapse, you burn at apoapse. If you want to increase your apoapse, you burn at periapse. Makes sense, right? If you want to increase things, you prograde. If you want to decrease them, you retrograde. I hope that makes sense. I'm going over kind of roughshod and slipshod at the moment. Don't worry if it doesn't make sense to you. I will end up doing a proper burn after this. I'm just going for a quick explanation so you can understand what I'm going to do next. We're also going to have a look at inclination. So, right now, we're pretty equatorial. I think this is a pretty good orbit. It's, generally, I think it was a good orbit. But what happens if we were to screw it up? Well, what effect does pointing normal have? As you might have guessed, since our orbit is on a 2D plane, how do you shift a 2D plane? Well, you point out of it. You point away from the 2D plane. So what we do is we point, if we can actually point at the point, normal or anti-normal. What happens is, if we have a look here, we're going in this direction currently. I mean, we'll come back and we'll go around. There isn't really a force pushing us up or down. If we were to impart a force pushing us up or down, you'll notice... Ta-da! We start to end up going up because the resultant of wanting to go this way and wanting to go this way is to go like that. As you can see. Now, inclination changes, let's talk about them for a minute. They take a lot of delta V. They can tell it, I'm going to tell you about delta V later. I don't want to throw too many terms at you. They take a lot of fuel. They can be very expensive in terms of your mileage. They are not, you can't really see that very well. There we go. They are not the most fuel friendly. They are not fuel efficient particularly. The best way to do a plane change, an inclination change, otherwise known as a plane change, would be when you are crossing the plane that you want to be on. So if we want to be in an equatorial, we'd want to find when the equator is, and then we'd want to, when we change over, when we go from being above the equator to below the equator, you'd want to do a burn then. So, now I've thrown a lot of stuff at you. I know I'm throwing a lot of stuff at you first of all, okay? Now, how do we fix this? Let's have a look. What is wrong with our orbit? Well, it appears the inclination is terrible. Who'd have thunk it? What else? Apoapse is 137, periapse is 99. What if we wanted 100 by 100? Or 200 by 200? Yeah, let's go for a 200 by 200. What if we want a 200 by 200 orbit? This is going to be tricky. Well, first of all, let's get onto the light side so you can actually see things a bit better. And I can't travel very fast. I definitely should go for 200 by 200. I can travel faster then. Well, first of all, the best way to sort things is, in my opinion, I think you really want to do the inclination first. It's probably the more complex thing to explain, but you really want to sort your inclination first. I think it's a lot easier to sort the inclination first and then deal with everything else. So, somewhere here, there will be a point where we cross the equator. Now, it's very hard to see, but it's about here. So what I'm going to do is I'm going to burn here. Now, we're going downwards at the moment. We're going descending, right? So this would be the descending node. What we need to do is burn at the descending node. So this is the point where we cross the equator. And because we're going down, we need to counteract it. We need to burn up. Okay? So what we need to do is wait for that. Now I'm estimating where this is, by the way, so it's not perfect. It's about here. And we need to burn normal. Yep, that's good. And we should see our orbit start to flatten out. There we go. You can see it coming down. Let's just get it a little bit better. Bam. And that's how you sort your inclination. Now, you could have some crazy inclination, but the principle still applies. You point normal or anti-normal in the direction that you want your orbit to flatten into, and you do it like that. Conversely, if you want to get a polar orbit, and you didn't launch into a polar orbit, launching into a polar orbit is a lot simpler. For that, you just point to the North Pole as you go up, as opposed to ascending over the sea. But yeah, or down. But yeah, if you wanted to do that from a equatorial orbit, you just keep burning, keep burning, keep burning, till you've pushed it over far enough. But that's how you do an inclination change. It's a bit simple. Simpler than you think, but you do have to estimate where that point is. So, if we're going for a 200-meter orbit, we need to get our apoapse and our periapse up. Doesn't really matter which one we do first. I think it's slightly more efficient if we did the apoapse first from the periapse. So what we're going to do at periapse is we're going to burn, because we're trying to get our apoapse up. So, to get the apoapse up, burn at periapse. What do? You want to increase it? You want to increase things? Prograde. Because you want to increase your height of your orbit, which means you need more speed, you need to get more velocity to get higher, you need to be able to counteract that pull of that planet that's keeping you close. You want to increase your speed. So what we're going to do at periapse, we're going to point to prograde, we're going to burn prograde. So, let's talk about timings of burns. So, if I were to click on my orbit here, you can see add maneuver. Awesome! And don't these little symbols look like things on the nav ball? Normal, anti-normal, anti-radial, radial, prograde, and retrograde. This one being retrograde. Those look familiar. What if I were to click and drag? It's showing me what my orbit would be if I did a burn of 736.1 delta V, 736.1 meters per second of delta V. Oh, cool. You can use this to estimate where you're going to move to. So if we were to just put this at, let's do a 300 orbit. That way it'll look a bit different. It'll be a bit easier to see, I think. 300. There we go. Oh, there we go. Perfect. 300.1 kilometers. Okay, cool. So what we need to do is we need to do a burn of 107.4 meters per second at this node. I think I've got a node. Bang on. Yeah, close enough. So, when you're doing a burn, the idea is that this theoretically is the amount. We'll talk about what it means in a minute. It's the amount you have to burn at that point. Literally at that second that the node happens. Not before, not after. In 4 minutes, 49 seconds, we will have to burn this much. Bam, done. But your engines don't do that. Your engines do thrust over time. They're like burning over time. If you could have an insanely powerful engine, you could do it in, a fraction of a second, bam, done. That'd be easy. But we don't. Actually, we do actually have an insanely powerful engine on this craft. It's kind of overspec'd. But the point being, you would have to normally, with engines, do prolonged burns. So if our burn will take us 20 seconds, it'll take us 20 seconds to do the burn it's asking for. You need to do this burn over the top of the time. So start 10 seconds before, finish 10 seconds after. Because you need to get the average on the point. Okay? So, let's talk about what this means. I know I'm throwing a lot of numbers at you. And, turns. But 107.4 meters per second of delta V. Okay, so what does delta V mean? Well, let's talk about why you need to know it. You need to know it because it's important. It is very important. It is what you talk about, the ability to travel different places. The ability to get from different orbits to other orbits is all about speed, and delta V is all about speed. It is what we talk about when we talk about the ability to get to different planets in KSP. It's the requirement, amount of fuel, and the engine you've got. Because different engines are more efficient, they've got different ISPs. You can't just say, you need more fuel. No, maybe you need a more efficient engine. Delta V is that number, because delta V is the amount you can change speed, because it literally means change in velocity. Delta being the Greek symbol for change, and velocity, delta V, V being velocity. So delta can be written as a delta symbol, which is a bit like a D, or a little triangle, which is the capital delta. Typically, there isn't really much difference. Generally, I think in maths I would have used a lowercase delta for small changes and a triangle uppercase delta for large changes, but it doesn't really matter. Typically written as a DV, because keyboards have a D on them but don't have a delta, and they look incredibly similar. So when you see D capital V, or even D lowercase v if someone's being a little bit fast with their typing, that means they're talking about delta V. Now, delta V is all about the ability to change speed. As you can guess, delta being change, V being velocity. So it's all about being able to change your speed. And why is this important? Well, as I've previously stated, you need to get a higher velocity to go up in your orbit, which means you could get a higher velocity to leave Kerbal sphere of influence and go to another planet. And then you need to slow down at another planet, so you need to do another change in speed. Now, that's the easy part. Some people will go, okay, isn't that just an acceleration? Acceleration, changing speed, that's an acceleration. No, an acceleration is meters per second squared, for instance. It's got another time component. Acceleration is the ability to do something in a certain amount of time. Delta V doesn't care how quickly you do something. Delta V says you can get there. Delta V doesn't say, you can only get there in 6 seconds or whatever. Delta V doesn't care about the time. You can do the burn fast, you can do the burn slow. It doesn't tell you how fast you will do that burn. It merely says you can do it. Okay? It's a very large concept to throw at you, but all you need to know for the moment is, Delta V is a thing. It is mentioned in the game here, but it's not mentioned anywhere else at the moment. In the future, this will be very important. In the future, it will be. Squad, the developers of Kerbal Space Program, have said they are going to add a Delta V readout to building rockets, and that will be incredibly useful. It is pretty much required, in my view, for playing the game. I always add mods, and a lot of people do, to show the Delta V when you're building a rocket, because it allows you to see, will the rocket make orbit, will the rocket get to here? It's basically like saying, I'm estimating the amount of fuel in my tank at the moment, and I don't know if I can make it to the gas station. Whereas with a Delta V mod, to be able to see it, and with the future additions that Squad are asking for, and probably going to implement, you will actually be able to know, I've got this much in my tank, I can go this far. It's very, very important. Knowing your Delta V is central to getting to different locations. And even just estimating it is important. But anyway, we have a node coming up in 40 seconds. Just bear in mind that for future. So, we're going to do our burn here. We're going to point prograde. And you can see we have, on the nav board, this blue marker. this blue marker is our maneuver node marker. It points in the direction that we have to burn to do the maneuver node. So let's just get ready. And burn. So the estimate was it would take just less than 20 seconds. It looks like it's good so far. Now the problem is we need to bang on stop our burn at the correct point. So I'm going to be a little bit on the ball for this one, but normally I'd recommend starting a little bit early and ending a little bit late, but just not going full throttle. There we go. I stopped a little bit late, but I can make up for that. And as you can see, the maneuver node is moving. Why is it moving, you say? Well, let's follow the maneuver node. This is what this button up here does, the one next to stability assist. When you have a maneuver node, it will give you a maneuver. Interesting. So why are we now pointing away from the retrograde? Well, it's because we overshot our retrograde. I'll come to this in a second. But if we... Alright, stopped allowing me to... There we go, come on. Bam, right. So we're within a tolerance and it says this is okay. There we go. And you see we have 300.39. That's acceptable. That's 0.1% almost. 0.1... something. 0.13. So we're pretty good there. Now the way we increase our periaps is pretty similar. We go to apoaps, and then we burn to increase our periaps. So we burn, we want to increase our speed over there? Cool, we increase prograde. So we go to apoaps and burn to increase our prograde. So, let's talk about radial anti-radial, because we haven't used radial anti-radial yet. What they do is they change the direction of your velocity, if I guess is that the way of terming it. If we were traveling this direction and we were to burn upwards, well, we'd start burning like that. So what would happen is our apoaps would come around because we'd end up going like that instead of like that. If we were to burn inwards, anti-radial, we'd end up going close to the planet, which would result in our periaps coming around because we'd end up going close to the planet. So burning anti-radial brings your periaps in, shifts the apoaps further around. Burning radial brings the apoaps towards you and the periaps away from you. So, that makes some sense in my head. I don't know how easily that's going to transfer to you in that terminology, but if I do a little burn like now, it's going to screw up our apoaps and our periaps a little bit, but you should get the idea. If I do a little burn, 1 point radial. There we go. So, burning radial, we're burning outwards, which means we're going to be increasing our height, so we're going to be pulling the apoaps towards us and pushing the periaps away. So, if we have a look, we're pointing away from the planet. You can't really see that very well, it's a bit dark, but here we go. Can you see the periaps is moving, and the apoaps is moving towards us? If we were to do the opposite, we would see the periaps come towards us. Now, normally you don't really do this very often by itself. You can do, but you wouldn't very often do it for doing something like an orbit like this because it doesn't offer very fine control. Or at least it's hard to get fine control. So we do this, bam, you can see we are pulling the periaps towards us, apoaps away. And we can decrease our apoaps like that and transfer it to our periaps. So, when you will use this is if you overshoot your apoaps or your periaps to the burn. So let's do a demonstration now. Let's have a maneuver node. Zoom in a bit, try and get this right. There we go. Periaps of 295, let's get that a little bit higher. 300 by 2994, that's fine. So what we're going to do is we're going to do this burn. It will want us to point prograde when we're at the apoaps, which will then become the periaps because we'll go ever so slightly over it. But let's do it late, and you'll see the effect, and it'll start asking us to burn a bit radial to make up for that. By the way, if you want to point at maneuver node early, because maneuver node is set compared to the maneuver node as opposed to any point on the orbit, which your current periaps is, your current prograde and retrograde is, you can point the maneuver node. And you see, like, we're meant to be pointing prograde here, but because prograde here is currently this direction over here for us, our prograde's over there, but our prograde from here would be over here, you can see that our maneuver node is actually pointing here. So we can actually time warp with the maneuver node, and we will find it will meet up with the prograde marker. Ta-da! So let's do our burn late. 23 seconds burn. And I should be doing the burn now. I should be middle of my burn in 4, 3, 2, 1. Oh, I'm doing my burn late. Watch what happens to the maneuver node. Marker. It will move to compensate for the fact I moved late. To bring the periaps back towards us. Or the apoaps back towards us. So if we accelerate a little bit. There we go. You can see the node is rising. Why is it doing that? Why is it doing that? Well, it's pointing out. Slightly radial. It's doing that because it's trying to bring the node back towards it. Okay? It's trying to increase our height here, which means it's trying to go back towards being apoaps. I don't know if that transfers as easily to you, but you will get used to it. This is a bit more of a complicated maneuver. I know it's lesson 2, but since we're doing more maneuvers, I threw it in here. It's a little bit more complicated, but we can burn up now, and it will account for it. If we were to burn more up, you can see our apoaps is coming back towards us. Let's just continue our burn, which, you know, I'm doing very slipshod, but right, so that is now 300.5, and this is 273. The problem is, if I continue burning, it's going to end up being much higher over here. So let's get rid of our maneuver node. So what do I need to do? Well, I could burn prograde, and if I burn prograde, you'll see that this will go up, and I'll get more than 300. And this will end up as probably about 290 is my guess, yeah. Well, I want to lose 6 from there, and I want to add 13 to there. How do I do this? Well, you can do it with the radial and anti-radial. So what do I want to do? I'm currently at about 300. This is at 306, and this is about 287. So what I want to do is I want to move some of my height from here to here. We can do that by pointing radial, because then we'll be pointing outwards, and it will push our periaps up. So let's just get there. And you can see, look, 288, 290, and this one is decreasing. 300. However, because you have to estimate where you're burning for this, it's not as accurate. It is, however, a pretty good way of sorting out a little bit of a wonky orbit. But if you're looking for getting perfect orbits simply, first time, and you've got no real time constraints, burn at apoaps and burn at periaps, because it's so much simpler. Because right now, I can burn at apoaps, and I can just buff my periaps. I know we've gone through a lot in this episode, and it might take maybe a couple of watches to really get it all sink in. I don't know. I've been playing this game for a very long time. But that should be a quick, brief intro to way too many things. So we've got 6 directions, which are 3 dimensions. We have prograde and retrograde. We have normal, anti-normal. We have radial, anti-radial. We have the sort of maneuver node system where you click, you have maneuver node, you drag, you can do inclination with it, you can do everything with it, and it'll be like, that will take you a lot. That was the kilometer of delta V. We can then right-click and delete that. We also have the ability to change our orbit, so we can do inclination burns, which you want to do when you're crossing the equator, if you're going for equator, or if you're going for another orbit when you're crossing that point. We can change our periaps by burning apoaps. We can change our apoaps by burning periaps. And if you really feel adventurous, you can do radial burns, although that is less often. Don't do radial burns unless you really need to sort something, or it doesn't really matter how much of a slipshod approach you get. But it's a good way of fixing a few things. So right now I managed to fix my orbit a little bit, and I can have my apoaps back. Because otherwise, if my periaps and my apoaps are wrong, I would have to burn at apoaps, and then I'd have to burn at periaps. Right now, I've burned a little bit, fixed my apoaps, and I can go to apoaps and burn my periaps. But that's it. Hopefully, this isn't too confusing. It does seem confusing to me going over it in my head, but if you're following along and you're actually playing the game while listening to this, or you go and straight apply this to the game and you try and use these 6 directions to orientate yourself, you should be okay. So if you've got a wonky orbit, fine. Inclination burn. Do a normal, do an anti-normal. Fine. You've got your periaps too high, Well, your apoaps too high. Your periaps can't be too high. It'd be your apoaps. If your apoaps is too high, sure, burn retrograde at periaps. Your periaps is too low, burn prograde at apoaps. That's how you do it. Hopefully you found this interesting. If you need any more clarification, go down to the comments below. I will try help out as much as I can. But until next time, if you found this enlightening, please remember to like it as a video and share it around or whatever. It really helps out so more people can see it and more people can get the tips. And if you're not subscribed, well, you want to see more, consider subscribing. But until next time, stay shiny. And next time, what should we do? Rendezvous? We'll do a rendezvous. People do seem to want a rendezvous. So we'll do a rendezvous tutorial, and then I think we'll do something about going to the moon.